Right now, 13 billion light-years away, a galaxy is dying before it should even exist. James Webb just spotted something impossible. A galaxy shining when the universe was barely 280 million years old. Black holes weighing billions of stars in a cosmos too young to birth them. Stars made of pure hydrogen erupting from total darkness. We thought we knew how the universe began. We were wrong. If you find this mind-bending, hit that subscribe button, because what you are about to discover will change everything you thought you knew about existence itself. Prepare yourselves. We begin. Picture yourself standing at the edge of time itself. That is exactly where James Webb Space Telescope took us in 2025. The galaxy has a name astronomers struggle to pronounce, MOMZ-14, but what it represents will shake you to your core. This ancient island of stars exists just 280 million years after the Big Bang. To put that in perspective, imagine compressing the entire history of the universe into a single year. We are seeing this galaxy on January 2nd. The universe barely had time to cool down from its violent birth. Yet there it was, blazing with the light of millions of young stars. Here is what makes your spine tingle. Light takes time to travel. Every second, light crosses 186,000 miles. The light reaching Webb right now left that galaxy 13.7 billion years ago. You are literally looking at a photograph of the infant universe. The galaxy appears tiny compared to our own, just 240 light-years across. That makes it 400 times smaller than the Milky Way. But its brightness defies explanation. Something inside is pumping out energy at levels that should be impossible. Webb's instruments detected the telltale signature of young stars being born at extraordinary rates. These are not gentle stellar nurseries. This is violent, explosive star formation happening faster than physics should allow. Scientists confirmed the discovery through spectroscopy. They split the light into its component colors like a cosmic fingerprint. The wavelengths told an unmistakable story. This light had been stretched by the expansion of space itself, redshifted to wavelengths 14 times longer than when it was first emitted. The discovery shattered the previous record by just 10 million years. But those 10 million years matter. Every moment closer to the Big Bang makes formation more mysterious, more impossible. Astronomers had predicted we might find galaxies this far back. Their predictions were conservative, cautious. They expected dim, small, struggling collections of stars. Instead, Webb found a powerhouse. The telescope revealed something else. The galaxy shows evidence of oxygen and carbon in its light signature. Those elements can only form inside stars. This means multiple generations of stars had already lived and died to create them. In just 280 million years, entire stellar life cycles had completed. Think about what that means. The first stars formed, burned through their fuel, exploded as supernovas, scattered heavy elements into space, and new stars formed from that enriched material. All before the universe celebrated its 300th million birthday. The light from this galaxy has traveled for so long that entire civilizations could have risen and fallen since it began its journey. Dinosaurs had not evolved when this light was already halfway here. But here is what astronomers whisper about late at night. If galaxies this bright and mature existed this early, what else is hiding just beyond our current limits? There is a wall at the edge of the universe, not made of matter, made of light itself. 380,000 years after the Big Bang, something extraordinary happened. The entire universe transformed in an instant. Astronomers call it the moment of recombination, and it created the oldest thing we can ever see. Before this moment, the cosmos was a furious soup. Free electrons scattered everywhere, bouncing photons around like ping-pong balls in a storm. Light could not travel even the tiniest distance. The universe was completely opaque, like trying to see through a wall of fog so thick you could cut it. Then the temperature dropped below a critical threshold. About 3,000 degrees, electrons suddenly paired with protons, forming the first stable hydrogen atoms. Light was finally free. That light has been traveling ever since, cooling, stretching, fading across 13.8 billion years. Today we detect it as microwaves, barely 3 degrees above absolute zero. The cosmic microwave background, the CMB. Two radio astronomers discovered it by accident in 1964. Arno Penzias and Robert Wilson thought pigeons nesting in their antenna caused the static. They cleaned out the droppings, shooed away the birds. The signal remained. They had found the echo of creation itself. The CMB surrounds us completely. It comes from every direction in the sky. If your eyes could see microwave radiation, the entire night sky would glow with a uniform haze. Not dark, but filled with ancient light. Satellites have mapped this light in exquisite detail. The temperature varies by only 1 part in 100,000 across the whole sky. These tiny ripples represent density fluctuations in the infant universe. Slightly denser regions, where gravity would eventually pull matter together to form galaxies. Every telescope, no matter how powerful, hits this wall. We can never see past it. The universe before recombination was fundamentally invisible, opaque, sealed from view by the laws of physics themselves. The CMB sits about 46 billion light-years away in all directions. Wait, you might think, how can something be 46 billion light-years away if the universe is only 13.8 billion years old? The expansion of space itself stretches distances. The light was emitted from regions much closer, but space has been expanding ever since, carrying those regions farther and farther away. Think of it like this. Imagine drawing dots on a balloon, then inflating it. The dots move apart, not because they are traveling across the balloon, but because the balloon itself is stretching. Space works the same way. Scientists measure tiny temperature differences across the CMB with incredible precision. Error bars, measured in millionths of a degree. The measurements match theoretical predictions so perfectly, it sends shivers down your arms. The Big Bang model predicted this radiation decades before we found it. But the CMB hides something profound. Everything that happened before recombination remains forever hidden. The first few 100,000 years of cosmic history occur behind an impenetrable veil. Unless we find another way to look, gravitational waves might let us peek further back, or neutrinos that traveled freely even through the opaque early universe. But photons? Light itself? The CMB is the absolute limit. Beyond that wall lies something we can never directly observe. The true beginning, 570 million years after the Big Bang, something impossible was already feeding. Webb spotted it in a galaxy called CANUCSLRDZ86. The numbers make your head spin, but what they found makes your understanding of reality crack apart. A supermassive black hole, actively growing, devouring matter faster than physics should permit. The black hole outweighs millions of stars. It sits at the heart of a galaxy that barely exists yet. The galaxy itself is still compact, still primitive, still learning how to be a galaxy. But this monster already rules it completely. Here is the problem that keeps astrophysicists awake at night. Black holes grow by eating. They pull in gas, dust, stars, anything nearby. But that process takes time. Lots of time. You cannot grow from nothing to millions of stellar masses in just 570 million years. The math simply does not work out. Even if a black hole formed immediately after the Big Bang and ate constantly at the maximum possible rate, it could not reach these masses this quickly. There is a physical limit called the Eddington limit. When material falls toward a black hole, it heats up and emits radiation. That radiation pushes back, creating outward pressure that slows down the feeding. Yet here sits this beast, already mature, already massive, already warping space around itself into bizarre knots. Webb found it through spectroscopy. The light signature showed highly ionized gas spinning rapidly around a central point, gas heated to millions of degrees. The unmistakable fingerprint of an accreting black hole, confirmed, no doubt. But the discoveries got stranger. Astronomers found another black hole, this one in galaxy GHZ2, possibly even earlier. 700 million years after the Big Bang. Again, impossibly massive. Again, impossibly mature. Then came the truly bizarre finding. A galaxy designated QS01, observed just 700 million years after the beginning. The black hole at its center weighs 50 million times more than our star, but the galaxy around it barely exists. Usually, galaxies outweigh their central black holes by thousands of times. Here, the black hole dominates. It is as if the black hole came first, and the galaxy is still trying to catch up. This flips everything backwards. We thought galaxies formed first, then black holes grew inside them. These observations suggest the opposite might sometimes be true. The black hole forms first, massive from the start, then attracts gas to build a galaxy around itself. Scientists call these heavy seeds. Instead of forming from the collapse of early stars, these black holes might have formed directly from massive clouds of primordial gas. Clouds weighing 100,000 times more than our star, collapsing straight into black holes without ever igniting as stars. It sounds like science fiction. It might be the only explanation that fits the evidence. Another black hole, designated Lid 568, was discovered feeding at 40 times beyond the theoretical limit. 40 times. That shatters every model we have. The radiation should blow away the infalling material. Instead, somehow, the black hole continues gorging itself. Every rule we thought governed black hole growth is being rewritten. The early universe operated under different conditions, more chaotic, more violent, more extreme, and we keep finding more of them. Imagine a star made of nothing but the two simplest elements in existence, pure hydrogen and helium. No carbon, no oxygen, no iron, nothing else. Just the raw ingredients of the Big Bang itself. These monsters might finally have been found. For decades, astronomers searched for population 3 stars, the first stellar generation, born in complete darkness 200 million years after the universe began. They would have burned unlike anything we see today. Without heavy elements, gas clouds could not cool efficiently. They stayed hot, turbulent, refusing to collapse into small stars. Instead, they formed absolute giants, stars weighing 30 to 300 times more than our star, burning millions of times brighter, living only a few million years before exploding catastrophically. These titans would have been the first light sources in all of creation. Their ultraviolet radiation would have torn through the surrounding hydrogen fog, ionizing atoms across vast distances. They were the torches that ended the cosmic dark ages, but we had never actually seen one, until possibly now. James Webb detected signatures in a galaxy called LAP-1b. The light from this galaxy traveled for 13 billion years to reach us. We see it as it appeared just 800 million years after the Big Bang. Inside this galaxy, gravitational lensing from a cluster called Max J 416 magnified the view by 100 times. The spectral analysis revealed something remarkable: extremely low metallicity. In astronomy, metals mean any element heavier than helium. This galaxy showed almost zero metals, 0.7% of what we see in our star. That is the signature of pristine, primordial star formation. The hydrogen and helium lines appeared clean, sharp, unmistakable. The pattern matched theoretical predictions for population 3 stars. They required Webb's unprecedented infrared sensitivity to detect. Ground-based telescopes could never have seen these faint signals. Here is what makes this discovery shake your foundation. These are not individual stars, they are stellar clusters, each weighing about 1,000 times our stellar mass, packed tight, burning furiously, flooding space with deadly radiation. These stars transformed the universe. Their explosions scattered the first heavy elements across space: carbon, oxygen, nitrogen, iron, all the ingredients needed for planets, for life, for you. Every atom in your body heavier than helium was forged inside stars. The first ones started that chain. Without gravitational lensing, we could never have spotted this galaxy. It would remain too faint, too distant, lost in the darkness. Einstein predicted gravitational lensing decades before technology could prove it. Mass bends space, and bent space acts like a lens, magnifying light from objects behind it. The cluster's gravity created a cosmic magnifying glass, bringing ancient light into focus. Webb combined multiple wavelengths of observation, near-infrared and mid-infrared, together painted the full picture. Scientists remain cautious. This is still being verified. Peer review continues. But if confirmed, this represents one of the most significant discoveries in astronomy. The first glimpse of the first stars, the objects that made everything else possible. These giants lived fast and died young. Their supernovas enriched the universe, seeding the next generation of stars with heavier elements. Each generation built on the last, eventually leading to stars like our own, to planets, to oceans, to life looking back at its origins. But wait until you hear what happened during those first few 100 million years of darkness. For hundreds of millions of years, the universe existed in perfect, absolute darkness. No stars, no galaxies, no light anywhere except the fading glow of the Big Bang itself, stretched into invisibility by the expanding cosmos. This was the cosmic dark ages, the longest night ever experienced by reality. 380,000 years after creation, the universe became transparent. Light could travel freely for the first time, but there was nothing to make light. The ingredients existed. Vast clouds of hydrogen and helium drifted through space, but they had not yet collapsed into anything luminous. Gravity worked slowly, patiently, pulling gas together into clumps. Dark matter, invisible but massive, created gravitational wells. Normal matter fell into these wells like water spiraling down a drain. But the process took time, cosmic time. During these dark ages, the universe cooled steadily. The temperature dropped from thousands of degrees to mere tens of degrees above absolute zero. The expansion continued relentlessly, carrying regions of space farther apart. Think about the silence, the stillness. No nuclear fusion anywhere. No stellar winds, no supernovas. Just cold hydrogen gas slowly, almost imperceptibly, gathering into denser and denser clouds. The dark matter halos grew first. These invisible structures formed the scaffolding on which everything else would build. They created the cosmic web, a vast network of filaments and nodes spreading across space like the neural pathways in a brain. Computer simulations can recreate this era. Scientists run models showing how tiny density fluctuations from the Big Bang grew into larger structures. The math works perfectly. The predictions match what we observe today. But actually seeing this period, impossible. No telescope can observe the dark ages directly. There was nothing to see. No light emission, no radiation signature, just neutral hydrogen gas that lets light pass through without interacting. Around 100 to 200 million years after the Big Bang, something changed. The first halos of dark matter grew massive enough, dense enough. The hydrogen clouds inside them collapsed. Temperature and pressure rose. And finally, after an eternity of darkness, nuclear fusion ignited. The first stars were born. These population 3 giants flooded their surroundings with ultraviolet light. The radiation ionized nearby hydrogen atoms, stripping away electrons. Bubbles of ionized gas formed around each star cluster. At first, these bubbles were small, isolated, scattered across the cosmos. But stars kept forming, more and more of them. The bubbles grew. They began to overlap, merging into larger ionized regions. This process, called reionization, would eventually transform the entire universe. The Dark Ages ended not with a single moment, but gradually, over hundreds of millions of years. Light pushed back the darkness, star by star, galaxy by galaxy, until finally, around 1 billion years after the Big Bang, the last neutral hydrogen was ionized. We can detect echoes of this transition. Radio telescopes search for the 21-centimeter line of neutral hydrogen. This specific wavelength tells us where neutral hydrogen exists. By mapping it across different distances, astronomers reconstruct the timeline of reionization. Projects like HERA, the Hydrogen Epoch of Reionization Array, use 350 radio antennas spread across South Africa. They listen for whispers from the Dark Ages, hoping to map how the first light spread through space. The Dark Ages were not empty. They were pregnant with potential. Every structure we see today, every galaxy cluster, every supercluster, traces its roots back to those silent centuries when gravity shaped the universe in darkness. What comes next transformed everything even more dramatically. 1 billion years after the Big Bang, the universe underwent surgery. Every single hydrogen atom in existence was torn apart and rebuilt. This was the epoch of reionization, the transformation that separated the ancient universe from the one we recognize today. It started quietly, with the first stars igniting. It ended with space itself fundamentally changed. Neutral hydrogen absorbs ultraviolet light. It acts like fog, blocking radiation from traveling far. The early universe was opaque to most wavelengths, but ionized hydrogen, split into separated protons and electrons, lets light pass freely. It becomes transparent. The first stars produced intense ultraviolet radiation. Each photon packed enough energy to knock electrons off hydrogen atoms. Around every star cluster, a bubble formed. Inside the bubble, ionized plasma. Outside, cold neutral gas. The boundary between them expanded outward as more hydrogen atoms were ripped apart. Think of it like streetlights turning on across a dark city. First one, then another, then dozens. Their pools of light spread and merge until the entire city glows. Reionization worked the same way, but on the scale of the universe itself. Scientists debate exactly when reionization completed. Current evidence suggests it ended between 650 million and 1 billion years after the Big Bang. Webb's observations are pushing that timeline earlier, creating tension with other measurements. The cosmic microwave background tells one story. The Lyman alpha forest, specific wavelengths of light absorbed by hydrogen, tells another. And now, Webb reveals far more early galaxies than expected, each pumping out reionizing radiation. The numbers do not quite match up. Something is missing from our models. One possibility involves recombination. Ionized protons and electrons can recombine back into neutral hydrogen. If this happened more often than we think, it would require more total radiation to complete reionization. The process would take longer, need more energy, involve more cycles of ionization and recombination. Black holes contributed too. Not just stars. Active galactic nuclei, powered by feeding supermassive black holes, emit enormous amounts of ultraviolet and X-ray radiation. Some models suggest these black holes did half the reionization work. Dwarf galaxies played an unexpected role. Webb observations revealed that tiny, faint galaxies were far more numerous than predicted. Each one contributed reionizing photons. Together, they outweighed the contribution from larger galaxies. The little ones did the heavy lifting. The topology of reionization matters. It did not happen uniformly everywhere. Some regions ionized faster because they had more stars. Others lagged behind. The resulting pattern looked like Swiss cheese. Ionized bubbles surrounded by neutral voids, gradually filling in the gaps. Radio telescopes try to map this topology by detecting neutral hydrogen across different distances. Each distance corresponds to a different time in cosmic history. By combining observations, astronomers reconstruct how the ionized regions grew and merged. The reionization epoch lasted hundreds of millions of years. That is fast on cosmic scales, but slow enough that we can potentially observe different stages. We can watch, in effect, as the universe transforms from opaque to transparent. This transformation heated the intergalactic medium. Ionized gas is hot gas. The energy from ultraviolet photons becomes heat when atoms are ionized. This heat affected how galaxies formed and evolved. It regulated star formation, influenced gas flows, shaped the large-scale structure we see today. Reionization also destroyed evidence of its own causes. The intense radiation blew away gas from small galaxies, shutting down their star formation. The galaxies that caused reionization often extinguished themselves in the process. But the most important effect? Reionization made the universe transparent. Light could finally travel across cosmic distances. Galaxies became visible to each other. The age of observation began. Yet some discoveries make reionization look gentle compared to what was really happening. In 2022, astronomers found galaxies that should not exist. They called them universe breakers. The name is not hyperbole. These galaxies formed too early, grew too massive, and shone too brightly. Every single one violates the standard model of cosmology. Every single one demands explanations we do not have. Standard theory predicts galaxy formation follows a slow, steady path. Small structures form first. They merge, gradually building larger and larger systems. This hierarchical growth takes billions of years. You cannot rush it. Physics sets the pace. Then Webb looked back to when the universe was less than 1 billion years old. The galaxies it found were massive, weighing as much as 100 billion stellar masses. That is comparable to our own Milky Way. Except these galaxies existed when the cosmos was barely 7% of its current age. One astronomer, Erica Nelson, from the University of Colorado Boulder, put it simply, "It's just absolutely wild. The galaxies show evidence of explosive star formation, not steady, controlled stellar birth, violent, chaotic bursts, creating millions of stars at once. Formation rates 100 times faster than our galaxy manages today. The light signature reveals young, hot stars, blue giants burning through fuel at incredible rates. The galaxies blaze with energy that should have taken far longer to accumulate. Scientists calculated how many ionizing photons these galaxies produced. The numbers came out wrong, 4 times higher than models predicted. If these bright galaxies were common in the early universe, reionization should have completed much sooner than we observe. Something in the theory is broken. Either the early universe was more chaotic and bursty than we thought, or galaxies can evolve far more quickly than physics allows. Some researchers suggest the star formation was not continuous. Instead, galaxies went through phases, intense bursts of activity followed by quiet periods. This episodic formation might pack more star creation into shorter timeframes. But even that barely explains what Webb sees. Others propose the initial mass function was different in the early universe. This function describes how many stars of each size form. Today, most stars are small and dim, but maybe in the ancient cosmos, more massive, bright stars formed. That would create brighter galaxies with less total mass. Dark matter might behave differently than we think. If dark matter halos formed faster or collapsed more efficiently, they could have pulled in normal matter more rapidly. That would accelerate galaxy growth. Or perhaps our entire cosmological model needs revision. Maybe the expansion rate of the early universe was different. Maybe dark energy played a different role back then. These possibilities terrify cosmologists because they require rewriting decades of established science. One galaxy, designated JADESGS Z140, became the poster child for this problem. It exists just 290 million years after the Big Bang. Yet, it is enormous, bright, and contains clear evidence of heavy elements. Multiple stellar generations have already occurred. Stars have formed, lived, died, and seeded new star formation, all in less than 300 million years. The galaxy is also forming stars at rates that seem unsustainable. Where does all the gas come from? How does it cool fast enough to collapse into stars? How do the stars avoid blowing away all the remaining gas with their radiation? Every answer raises more questions. These universe breakers are not rare exceptions. Webb keeps finding them. Dozens have been identified. They represent a genuine population of objects, not just flukes or measurement errors. The astronomy community is split. Some think the observations will be refined and the problem will resolve. Others believe we are on the verge of a revolution in cosmology, a fundamental shift in how we understand the universe's first billion years. One thing is certain: the early universe was wilder than anyone imagined. Webb keeps spotting them, tiny objects in the early universe, glowing red in infrared light. Astronomers have a technical term for them: little red dots, LRDs, and nobody knows what they are. These objects are small, compact, intensely luminous. They appear at vast distances, existing when the universe was less than 1 billion years old. Their colors place them firmly in the infrared, red-shifted by cosmic expansion. Here is what makes them mysterious. Their spectra do not match anything we understand. Some features suggest active star formation. Other features indicate supermassive black holes. Some signatures hint at both simultaneously. The data contradicts itself. One possibility is that each LRD contains a feeding black hole surrounded by intense star formation. The black hole provides X-ray emission. The stars produce ultraviolet light. Together, they create the strange combined spectrum. But the geometry is all wrong. If you put a black hole inside a star-forming region, the black hole's radiation should disrupt star formation. The energetic photons heat the surrounding gas, preventing it from collapsing into new stars. You should not see both processes happening together. Another theory suggests LRDs are heavily obscured black holes. Dust surrounds them, absorbing the black hole's light and re-emitting it in the infrared. This could explain the red color, but the amount of dust required seems excessive for such young galaxies. Some astronomers propose an exotic explanation: black hole stars, hypothetical objects where a black hole sits inside a massive star, feeding on it from within. The black hole provides energy, while the star's outer layers provide the visible structure. This sounds like science fiction. It might be science fact. Galaxy CANUCSLRDZ86 is one of these mysterious objects. Spectroscopy confirmed a rapidly feeding supermassive black hole at its core. The black hole grows faster than models predict. The galaxy itself is compact, barely producing heavy elements, clearly in early stages of evolution. The black hole outweighs what the galaxy should be able to build so quickly. This pattern repeats across many LRDs. Disproportionately massive black holes in undersized galaxies, as if the black holes formed first and the galaxies are playing catch-up. Dozens of LRDs have been catalogued now. They appear far more common than expected. Webb finds them everywhere it looks in the early universe. This abundance creates its own mystery. If LRDs are rare exotic objects, why are there so many? Some researchers think LRDs represent a brief evolutionary phase that all early galaxies pass through. A stage lasting only a few tens of millions of years, when the central black hole dominates before the galaxy has time to grow. We catch them in this phase, because Webb happens to be looking at exactly the right epoch. Others believe LRDs might be connected to the formation of supermassive black hole seeds. The mysterious heavy seeds that explain how black holes reach massive sizes so quickly. If these seeds form through direct collapse of gas clouds, the early stages might look exactly like what Webb observes. The dust content in LRDs is puzzling too. Dust forms from elements created in stars. Supernovas scatter dust across space. But LRDs exist so early that there has barely been time for supernovas to occur. Where did the dust come from? Perhaps the first stars, population, 3 giants, produced dust when they exploded. Their supernovas were far more powerful than modern stellar explosions. They might have created and dispersed enormous quantities of dust very quickly. Or maybe we are seeing dust formed through different processes. Cooling black hole winds might condense heavy elements directly into dust grains. Turbulent gas flows could facilitate dust formation through mechanisms we do not yet understand. Each new Webb observation adds data to the puzzle, but the picture remains frustratingly incomplete. These little red dots are trying to tell us something fundamental about how the universe works. We just have not learned their language yet. 5 quasars. Ancient, brilliant, powerful. James Webb found them sitting alone in the void, Quasars are supermassive black holes feeding voraciously. They shine with the light of trillions of stars. Material spiraling into the black hole heats to millions of degrees, emitting radiation across the entire electromagnetic spectrum. They are the brightest persistent objects in the universe. Every model of quasar formation says the same thing. They should exist in the densest regions of the cosmos, where galaxy clusters form, where dark matter halos overlap, where abundant matter provides fuel for the black hole's growth. Webb looked at 5 quasars from 600 to 700 million years after the Big Bang. These are among the oldest quasars known. The team from MIT expected to see them surrounded by galaxies, dense neighborhoods packed with star-forming systems. Instead, they found mostly emptiness. One quasar had about 50 neighboring galaxies. That matched predictions. But the others existed in relative isolation. Only a handful of nearby systems. Some appeared to sit in the middle of nowhere. Anna Christina Eilers, the lead researcher, expressed the confusion perfectly. Contrary to previous belief, we find on average these quasars are not necessarily in those highest density regions of the early universe. Some of them seem to be sitting in the middle of nowhere. It's difficult to explain how these quasars could have grown so big if they appear to have nothing to feed from. The cosmic web of dark matter forms a predicted structure. Computer simulations map it in detail. Quasars should sit at nodes where multiple filaments intersect, the highest density locations. Yet, these observations show quasars scattered across the web, sometimes in relatively empty regions. How does a black hole grow to 1 billion stellar masses without nearby matter? The accretion process requires continuous supply of gas, dust, and stars. If the quasar sits in a sparse region, where does the fuel come from? One possibility offers some comfort. Maybe the galaxies are there but hidden, shrouded in dust so thick that even Webb cannot see them. The dust absorbs visible and ultraviolet light, re-emitting it in the far infrared. Current observations might miss these dust-enshrouded galaxies. Future observations will test this idea. Webb can tune its instruments to see through dust by observing at longer wavelengths. If hidden galaxies exist, we should find them. But what if the galaxies truly are absent? What if these quasars really do sit alone? That would require completely rethinking how supermassive black holes form and grow. Maybe they formed as heavy seeds, massive from the start, born from direct collapse of giant gas clouds. They would not need to grow much to reach the masses we observe. They started big, or perhaps the quasars are older than they appear. If they formed during the Dark Ages, before stars and galaxies became common, they had extra time to accumulate mass from diffuse gas spread throughout space. Another radical idea suggests the black holes moved. Maybe they formed in dense regions, grew massive, then got kicked out through gravitational interactions. Mergers between massive objects can produce recoil, flinging one object away at high velocity. The quasar might have traveled far from its birthplace. The 5 quasars show tremendous variety, some in crowded fields, some alone. This diversity itself is puzzling. If all quasars form through the same process, they should all exist in similar environments. The mixed observations suggest multiple formation pathways. Every quasar Webb observes adds another piece to the puzzle. The team plans to study more distant quasars, mapping their environments, searching for patterns. They will observe in multiple wavelengths, looking for hidden structures. For now, the lonely quasars remain an enigma, bright beacons in the ancient universe, shining without obvious fuel sources. What they reveal about the first billion years might completely overturn our cosmic timeline. Everything you learned about galaxy formation might be backwards. For decades, the sequence seemed obvious. First, galaxies form, stars ignite, cluster together, create gravitational centers. Then, over time, a black hole develops at the core. Gas funnels inward, a small black hole forms from stellar collapse, and it gradually grows by consuming nearby matter. The black hole is a consequence of the galaxy, a byproduct. something that emerges after the main structure exists. Webb just found evidence that the opposite sometimes happens. Galaxy QSO-1 exists 700 million years after the Big Bang. At its center sits a black hole weighing 50 million times our stellar mass, confirmed through multiple observations. No doubt about its existence or size, but the galaxy around it barely registers. The stellar mass is tiny compared to the black hole. Usually, galaxies outweigh their central black holes by a factor of 1,000. Here, the black hole dominates completely. It is as if someone built the engine before the car. The black hole exists, massive and mature, while the galaxy struggles to assemble itself. The light signature reveals very little gas and very few stars. The system lacks the material that should surround a normal galaxy. It defies the standard mass relationship between black holes and their hosts. Marta Volonteri, a leading expert on black hole formation from the Paris Institute of Astrophysics, studies cases like this. She notes that models once considered exotic might actually be the norm. What we used to call exotic models are perhaps not so exotic anymore. If black holes can form before galaxies, the entire timeline shifts. Maybe massive black holes emerged directly from collapsing gas clouds during the Dark Ages. They formed first, then attracted more gas through their gravity, slowly building a galaxy around themselves. This heavy seed model explains the impossible masses. If black holes start at 100,000 stellar masses, they have a massive head start. They do not need to grow as quickly. The time problem disappears. The discovery of multiple such systems suggests this is not rare. It might be common in the early universe. Different formation pathways operating simultaneously. Some black holes form inside galaxies, growing slowly from stellar remnants. Others form first, seeding galaxy formation around them. Both processes create the supermassive black holes we see today. This changes how we think about galaxy evolution. The black hole is not just along for the ride. It plays an active role. Its gravity helps gather material. Its radiation regulates star formation. Its winds blow away gas or trigger new stellar birth. The relationship between black holes and galaxies is not parent and child. It is symbiotic. They evolve together, influencing each other, shaping each other's growth. Modern galaxies all show a tight correlation: black hole mass versus stellar mass, a predictable relationship that holds across billions of galaxies. This relation exists even in the ancient universe. The earliest quasars and their host galaxies follow the same pattern. This similarity is weird. If the early universe was chaotic, wild, different from today, why do the black hole galaxy relationships look identical? Something fundamental links these two masses. Some mechanism enforces the correlation regardless of when or how the system forms. Scientists think feedback processes maintain the balance. When a black hole grows too large, its radiation prevents more gas from falling in. Star formation slows. The galaxy stops growing. When the black hole is too small, the galaxy can keep forming stars and feeding the black hole. Eventually, they reach equilibrium. But if black holes sometimes form first, that challenges this feedback model. A massive black hole without a galaxy, yet, should behave differently. It should suppress galaxy formation entirely, yet somehow, galaxies still form. The observations raise more questions than answers. How common are black hole first systems? Under what conditions does this pathway dominate? How quickly do the galaxies catch up in mass? Webb continues monitoring these systems. Long-term observations will track their evolution, watching as the galaxies grow around their oversized black holes. One thing becomes clear. The early universe was not a slower, simpler version of today. It was fundamentally different, operating under conditions we barely comprehend, and the black holes growing in that ancient chaos were stranger than anyone imagined. There is a speed limit in the universe, a hard cap on how fast black holes can grow. It is called the Eddington limit, and it is based on fundamental physics. Then astronomers found LID 568, and the limit shattered. The black hole is feeding at 40 times the theoretical maximum rate. 40 times. That should be impossible. The laws of physics should prevent it. Yet there it is, confirmed through multiple observations, devouring matter faster than reality allows. Here is how the Eddington limit works. Material falling toward a black hole does not fall straight in. It forms an accretion disk, a swirling spiral of superheated gas. Friction heats this gas to millions of degrees. At those temperatures, it emits intense radiation. That radiation creates pressure. Photons carry momentum. When they hit in falling material, they push back. At a certain feeding rate, the outward radiation pressure exactly balances the inward gravitational pull. That is the Eddington limit. Try to feed faster, and the radiation blows away the incoming material. Every black hole in the modern universe respects this limit. You cannot break it. It is like trying to fill a cup while simultaneously blowing air into it. Eventually, the air pressure prevents more water from entering. Lid 568 somehow found a loophole. The black hole sits in a dwarf galaxy just 1.5 billion years after the Big Bang. It is low mass for a supermassive black hole, weighing millions rather than billions of stellar masses. But its feeding rate is off the charts. Chandra X-ray Observatory detected intense X-ray emission from the source. Webb followed up with infrared spectroscopy. The combined observations painted an unmistakable picture. Matter is pouring into this black hole at rates that should be physically impossible. Scientists hypothesize the black hole is undergoing super Eddington accretion, a brief phase, probably lasting only a few million years, where the normal limits do not apply. During this phase, the black hole can grow tremendously. How? The geometry might be key. If the accretion disk is thick and puffy rather than thin and flat, radiation might escape through holes instead of pushing back on all the infalling material. Think of it like a sponge. Light leaks through gaps while matter continues falling through other channels. Another possibility involves the spin of the black hole. A rapidly spinning black hole warps space around itself. This warping can change how radiation interacts with infalling matter. The Eddington limit might be higher for spinning black holes under certain conditions, or perhaps the material falling in is unusually clumpy. Instead of a smooth flow, the black hole encounters dense clumps of gas. Each clump falls in quickly, before radiation pressure has time to build up and push it away. Between clumps, the radiation escapes. The average feeding rate appears to exceed the Eddington limit, even though instantaneous rates remain below it. This discovery provides critical insights into how supermassive black holes reach their enormous masses. If normal feeding were the only pathway, black holes could not grow fast enough. But super Eddington accretion changes the calculation. A black hole experiencing episodes of superfast feeding can accumulate mass much more quickly. The early universe might have been full of black holes undergoing similar feeding frenzies. We just happened to catch lid 568 inches the act. Most such episodes end after a few million years. The black hole blows away remaining gas, starving itself, entering a quieter phase. We see only the ones actively feeding. If super Eddington accretion was common, it explains the existence of billion-mass black holes so early in cosmic history. They did not grow at the Eddington rate. They grew much, much faster during multiple episodes. The radiation from LID 568 is extraordinary. If you could somehow stand at a safe distance and observe, the black hole would outshine everything else in its galaxy combined. The accretion disk blazes brighter than trillions of stars. But that brightness is temporary, a flash in cosmic time. Soon, perhaps already by now, since we see it as it was in the past, the black hole will quiet down. The super Eddington feast will end. Normal feeding resumes until the next episode, because if it happened once, it can happen again. Black holes might cycle through these phases repeatedly, each time adding significantly to their mass. We are watching physics push itself to the absolute edge of possibility, the universe testing its own limits and somehow, occasionally, exceeding them. What other limits are more flexible than we think? 740 million years after the Big Bang, two monsters were already dancing toward destruction. Webb observed the system designated ZS7. Two supermassive black holes, each weighing millions of stellar masses, locked in a death spiral. They orbit each other, gradually pulling closer, destined to merge in a catastrophic collision. This is the earliest black hole merger ever detected. The discovery pushes the timeline of black hole growth into entirely new territory. Black hole mergers are violent beyond description. As the two objects spiral inward, they emit gravitational waves, ripples in space-time itself, spreading outward at the speed of light. The waves carry energy, causing the orbits to decay. The black holes spiral faster and faster until finally they collide. The merger releases more energy than all the stars in a galaxy produce over millions of years, all released in seconds. A cataclysmic explosion in the very fabric of space. Gravitational wave detectors like LIGO detect mergers of small black holes, weighing just tens of stellar masses, happening in the modern universe. But supermassive black hole mergers require different instruments. The waves have much longer wavelengths. Ground-based detectors cannot see them. The future space-based detector, LISA, will specialize in detecting supermassive black hole mergers. When LISA launches, it will listen for events like the ZS7 merger, but happening in real time. The discovery of ZS7 means LISA will have plenty to detect. These mergers were apparently common in the early universe. Webb spotted ZS7 through spectroscopy. The light signature showed two distinct sources of emission, each with the characteristic spectrum of an accreting black hole. Dense gas rotating at extreme speeds, high ionization indicating intense radiation, multiple emission lines revealing hot, turbulent material. The researchers measured fast-moving gas with specific spectral features. Ionized hydrogen moving at thousands of miles per second. These velocities reveal the presence of two massive objects orbiting a common center. The separation between the black holes is still relatively large, probably hundreds of light years. At their current rate, they will merge in tens of millions of years. But on cosmic scales, that is essentially immediate. Mergers like this dramatically accelerate black hole growth. When 2 million mass black holes merge, they create a 2 million mass black hole. Simple addition, but it happens quickly, much faster than growing through accretion. If mergers were common in the early universe, they provide a pathway to build supermassive black holes rapidly. The discovery also reveals that massive black holes existed in pairs very early. They must have formed in separate galaxies. Then those galaxies collided and merged. The black holes inherited the orbital motion of their host galaxies, eventually settling into mutual orbit. Galaxy mergers were far more common in the early universe. Structure was forming, small systems colliding and combining into larger ones. Every merger potentially brought two black holes together. The early universe was a demolition derby of colliding galaxies and merging black holes. Evidence of past mergers shows up in modern galaxies too. The Milky Way contains stellar streams, remnants of smaller galaxies torn apart and absorbed. Each absorbed galaxy might have brought its own black hole. Our galactic center might have grown partly through mergers. The ZS7 system challenges models again. How did two massive black holes exist at this early time in close enough proximity to merge? Both had to form and grow to millions of masses. Their host galaxies had to collide, and the black holes had to begin their spiral, all within 740 million years. It is barely enough time. Every step has to happen with maximum efficiency. Formation, growth, collision, merger. No delays, no interruptions. Webb's capability to detect such systems revolutionizes our understanding. Before Webb, we could not see this far back with enough detail to identify merging black holes. The infrared sensitivity makes the impossible possible. More merger systems will be discovered. Webb has only begun surveying the early universe. Each observation reveals new surprises. Each surprise demands explanations. The ZS7 black holes are dancing their final dance. They will circle each other, draw closer, emit gravitational waves, and finally collide in a burst of warped spacetime. By the time their light reaches us, the merger has already happened. Billions of years ago, those two became one. But we can still watch, still learn, still try to understand how the universe built its most powerful engines of destruction. Star formation takes time. Gas clouds collapse slowly. Stars ignite gradually. Galaxies build over eons. That is the rule. Then Webb observed galaxies churning out stars 100 times faster than our Milky Way manages today. These are not minor differences, not slight variations in efficiency. We are talking about galaxies forming stars at rates that physics struggles to explain. Formation so rapid it challenges our understanding of how stars are even made. Our galaxy, the Milky Way, forms roughly 1 to 2 new stars per year. That rate has held steady for billions of years. It is controlled by the availability of cold gas and the efficiency of cloud collapse. You cannot go much faster without running out of material or heating the gas too much. But these early galaxies, they are forming stars at rates of 100 to several hundred per year. The entire galaxy blazes with stellar nurseries. Everywhere you look, new stars ignite. Where does all the gas come from? Star formation consumes gas rapidly. Hydrogen and helium in clouds collapse to form stars. Those stars emit radiation that heats surrounding gas, preventing more collapse. The system self-regulates. Formation rates cannot increase indefinitely, yet somehow, these galaxies keep the fuel flowing. Gas streams in from intergalactic space, feeding the star formation furnace. Gravity channels material along cosmic web filaments, delivering fresh supplies to the galaxies. The accretion continues non-stop. The radiation from so many young stars should blow gas away. Stellar winds and supernova explosions inject energy and momentum. They create bubbles of hot gas that expand outward, clearing regions of star-forming material. This feedback normally limits how fast stars can form. In these early galaxies, feedback apparently fails, or operates differently. Maybe the gas is so dense that even powerful stellar winds cannot disperse it. Maybe the galaxies are so massive that their gravity holds everything in place despite the radiation pressure. The metallicity of these galaxies offers clues. Metals, elements heavier than helium, come from stars. The first generation of stars dies and produces metals. Those metals enrich the next generation. Metallicity increases over time as more stellar cycles complete. Early galaxies show surprisingly high metallicity, not as high as modern galaxies, but far higher than they should have after existing for only a few 100 million years. Multiple generations of stars have formed and died already. The cycling happens incredibly fast. Supernovas from massive stars enrich the gas with carbon, oxygen, nitrogen, iron. This enriched gas forms new stars. Those new stars also contain metals, which affect how they burn, how they emit light, how they evolve. The presence of metals changes everything about star formation. Some astronomers think the initial mass function was different. Today, most stars are small and long-lived. For every massive star, hundreds of small stars form. But maybe in the early universe, the ratio shifted. Maybe more massive stars formed. They would burn brighter, produce more metals, and die faster in spectacular supernovas. This top-heavy initial mass function would explain the extreme brightness and rapid enrichment. Massive stars flood the galaxy with light and heavy elements. They create the observed signatures, but they die quickly, within just a few million years. The star formation has to continue at furious rates to maintain the population. The morphology of these galaxies looks chaotic. They lack the organized spiral arms or elliptical symmetry of modern galaxies. Instead, they appear clumpy, irregular, turbulent. Star formation concentrates in dense knots scattered across the galaxy. Each knot blazes with thousands of new stars. This clumpy formation might be more efficient. Instead of spreading star formation across the entire disk, it concentrates in small regions where gas density is highest. Each clump forms stars rapidly before feedback disperses it. New clumps form elsewhere. The overall rate stays high, even though individual regions turn on and off. Galaxy mergers drive some of this activity. When two gas-rich galaxies collide, their gas clouds slam together. The collision compresses the gas, triggering intense star formation. Merger-driven starbursts can create formation rates hundreds of times higher than normal. In the early universe, mergers happened constantly. Galaxies had not settled into stable configurations. They continued colliding, merging, exchanging material. Each collision sparked new rounds of star formation. These hyperproductive galaxies might explain another mystery. Where did all the stars in massive modern galaxies come from? They needed precursors, forming stars at extreme rates. These early starbursts might be exactly those precursors, but watching them challenges everything. Seeing formation this fast forces us to reconsider whether we understand stars at all. You are sitting at the center of a sphere. A sphere, 46 billion light-years in radius. Beyond that boundary, nothing can ever reach you. No light, no signal, no information. That is the edge of the observable universe. Wait, the universe is 13.8 billion years old. How can the edge be 46 billion light-years away? Simple math says light could only travel 13.8 billion light-years in that time. But space itself expands. The light that reaches us today was emitted from regions much closer. While the light traveled toward us, space stretched, carrying the source farther away. By now, the galaxy that emitted that light sits 46 billion light-years distant. This creates a hard limit. Objects beyond this distance are receding faster than light can approach us, not because they are moving through space at light speed, but because the space between us stretches faster than light can cross it. Imagine an ant walking on a rubber band while you stretch the band. The ant walks forward, but the band stretches faster than it walks. The ant never reaches the far end. Light faces the same problem at cosmic scales. This boundary is called the particle horizon. It marks the farthest distance from which light has had time to reach us since the Big Bang. Anything beyond it remains forever invisible, not because light cannot escape it, but because insufficient time has passed for the light to complete its journey. The observable universe is just one region of a vastly larger cosmos. Most of the universe lies beyond our view, unreachable, unknowable, existing but forever separate from us. The expansion of space is accelerating. Dark energy, a mysterious force making up 68% of the universe's content, drives this acceleration. As space expands faster and faster, the observable universe's effective size actually shrinks in some sense. The future light cone gets smaller. Billions of years from now, distant galaxies we see today will cross beyond the boundary. Their light will redshift to infinite wavelengths. They will fade from view, disappearing past our horizon. Eventually, only our local group of galaxies will remain visible. Everything else will recede beyond reach. But for now, Webb pushes against the current boundary. It looks outward to the very edge of what is observable. The most distant galaxies it sees exist near the limit. Their light left them when the universe was just a few 100 million years old. Since then, space has expanded so much that those galaxies now sit near the 46 billion light-year mark. Some galaxies we observe are moving away faster than light. That sounds impossible. But special relativity only forbids objects moving through space faster than light. Space itself can expand at any rate. No speed limit applies to the expansion. As a result, the galaxies we see in Webb's images exist in a strange limbo. We see them as they were billions of years ago, but their current state is forever hidden from us. We can never know what they look like now. By the time light showing their current state reaches us, billions more years will have passed, and they will have changed again. We observe only the past. The present of distant objects is unknowable. The universe shows us not how it is, but how it was. Webb is a time machine, looking backward across cosmic history. Every image shows the ancient universe, frozen in moments that ended billions of years ago. This temporal disconnect creates philosophical puzzles. What does it mean for something to exist if we can never observe its current state? The galaxy exists now, somewhere out there, 46 billion light-years away, but we can never see it as it is now, only as it was 13 billion years ago. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains billions or trillions of stars. The total number of stars exceeds the number of grains of sand on all of Earth's beaches. And this is just the observable portion. The total universe is almost certainly far larger. Some theories suggest the universe is infinite. If so, the observable universe is just a finite bubble in an infinite expanse. Beyond our horizon, an infinite number of galaxies, stars, and planets exist that we can never see. Other theories propose a finite but unbounded universe. Like the surface of a sphere, it curves back on itself. Travel far enough in one direction, and you eventually return to your starting point. In this model, the universe has a finite volume but no edge. We may never know which is true. The boundary of observation limits what we can test. Beyond the horizon, physics remains the same, but evidence becomes unobtainable. Science can speculate, but cannot prove. Yet, even within the observable universe, mysteries abound, and the edge holds the deepest secrets of all. Sometimes, the universe provides its own magnifying glass. Massive galaxy clusters warp space-time so severely that they bend light around themselves, creating cosmic telescopes capable of revealing objects otherwise too faint to see. This is gravitational lensing, and it revolutionizes our ability to observe the ancient universe. Einstein predicted it in 1915. His general theory of relativity showed that mass curves space-time. Light follows the curves. When light from a distant galaxy passes near a massive object, it bends around that object. The path curves, the image distorts, and sometimes the light is magnified. Think of looking at something through the base of a wine glass. The curved glass bends light, distorting and magnifying the image. Gravitational lensing works similarly, except the lens is made of dark matter and galaxies, and the magnification can reach factors of 100 or more. Galaxy clusters are ideal lenses. They contain thousands of galaxies, enormous quantities of hot gas, and vast halos of dark matter. Their total mass can equal millions of billions of stellar masses. All that mass concentrated in one region creates profound space-time curvature. Cluster Max J 416 lies about 4 billion light-years from Earth. Webb uses it as a natural telescope to observe galaxies far beyond. Objects behind the cluster, from our perspective, have their light bent and magnified as it passes through the cluster's gravitational field. This magnification revealed the population 3-star candidates in galaxy LAP-1b. Without the cluster's lensing effect, LAP-1b would be far too faint for even Webb to detect. The cluster amplified its light by a factor of 100. Suddenly, the ancient galaxy became visible, its secrets accessible. The magnification is not uniform. Different regions of the cluster lens differently. Some areas create multiple images of the same background galaxy. Light takes different paths around the cluster, arriving at our telescopes from multiple directions. We see the same galaxy several times, each image distorted differently. Astronomers use sophisticated models to map the cluster's mass distribution. By understanding how matter is arranged, they can predict exactly how light will bend. These models reveal the location and properties of dark matter, which contributes most of the lensing effect. Sometimes lensing creates Einstein rings. When alignment is perfect, the background galaxy's image stretches into a complete circle around the lensing cluster. The ring is actually a single distorted image of a galaxy directly behind the cluster's center. More commonly, lensing produces arcs, curved streaks of light appearing around the cluster. Each arc is an extremely magnified and distorted galaxy. By analyzing the arcs, astronomers reconstruct the true shape and properties of the background galaxy. The time delay is another fascinating effect. Different light paths have different lengths. Light taking a longer path arrives later. If the background galaxy varies in brightness, we see those variations at different times in different images. This time delay helps measure cosmic distances and the expansion rate of the universe. Gravitational lensing also affects our search for the most distant objects. Faint galaxies from the early universe become detectable only when magnified by foreground clusters. Webb surveys multiple massive clusters, using each as a cosmic magnifying glass. Cluster Abell 2744, nicknamed Pandora's cluster, provides another powerful lens. It contains the remnants of multiple cluster collisions. The complex mass distribution creates extreme lensing effects, magnifying background galaxies by factors of 10 to 30. The future of extremely distant astronomy relies heavily on lensing. Next-generation telescopes will continue exploiting this natural phenomenon. By finding the right lenses, we can observe galaxies and stars that would otherwise remain forever invisible. But lensing has limits. It magnifies but also distorts. Reconstructing the true properties of a lensed object requires sophisticated analysis. The magnification varies across the object's surface, stretching some parts more than others. Separating true structure from lensing artifacts is challenging, and lensing only works when alignment permits. The lens must sit between us and the target, perfectly positioned. Such alignments are rare. For every object magnified by lensing, thousands remain too faint to see. Still, gravitational lensing gives us a window into the otherwise unreachable past. It extends our vision beyond the capabilities of any telescope. The universe itself becomes our instrument, allowing us to see farther, deeper, earlier than we ever could alone. What we find through these cosmic magnifying glasses continues to astonish us. Modern galaxies follow a rule, a strict, predictable relationship between the mass of the central supermassive black hole and the total mass of stars in the galaxy. The black hole weighs about 1/1000th of the stellar mass. This ratio holds across billions of galaxies, spanning vast ranges of size and age. Nobody knows why. It suggests something fundamental links black hole growth and galaxy growth. They evolve together, regulating each other's development. When the galaxy adds mass, the black hole grows proportionally. When the black hole feeds, it affects star formation throughout the galaxy. But here is what shakes your understanding. This relationship exists in the ancient universe too. Galaxies observed less than 1 billion years after the Big Bang show the same mass ratio. The correlation appears immediately in the first galaxies and black holes to form. Webb observations of early quasars revealed this shocking fact. The team measured stellar masses by analyzing light from the host galaxies. They measured black hole masses by studying the accretion disk emission. The two masses follow the modern relationship almost exactly. This should not work. The early universe was chaotic, turbulent, completely different from today. Galaxies had not settled into stable structures. Black holes were still figuring out how to grow, yet somehow they maintained the same mass balance we see 13 billion years later. The relationship implies a feedback mechanism. When the black hole grows too large for its galaxy, something stops its growth. When the galaxy grows faster than the black hole, something accelerates black hole feeding. The two balance each other. Active galactic nuclei provide one type of feedback. When a supermassive black hole feeds actively, it emits enormous energy, radiation and jets heat surrounding gas to millions of degrees. This hot gas cannot collapse to form stars. Star formation throughout the galaxy slows or stops. Eventually, the black hole runs out of nearby fuel. It enters a quiet phase. The gas cools. Star formation resumes. The galaxy catches up in mass. Then something, a galaxy merger perhaps, funnels more gas to the center. The black hole reactivates. The cycle repeats. This feedback keeps the masses in balance. The black hole cannot grow too large without shutting down its own food supply. The galaxy cannot grow too massive without feeding its central black hole enough to trigger feedback. But why does this mechanism work in the early universe just as well as today? The conditions were completely different. Gas was denser, merger rates were higher, star formation proceeded at extreme rates. Yet the same ratio emerges. One possibility is that the ratio is set during the initial formation of the system. However, the black hole and galaxy first form, they establish the mass relationship immediately. It persists because the feedback mechanisms maintain it regardless of conditions. Another theory suggests the dark matter halo mass determines both the galaxy mass and black hole mass independently. Both depend on the halo, creating a correlation between them, even though they do not directly influence each other. This would explain why the relationship holds across all epochs. Computer simulations attempt to reproduce the correlation. Models that include black hole feedback successfully create the observed ratio in simulated galaxies, but fine-tuning is required. The feedback strength must be precisely calibrated. Too weak, and black holes grow too large. Too strong, and galaxies do not form enough stars. The early observations from Webb test these models. If simulations predict the ratio should be different in the ancient universe, they are wrong. The observations show otherwise. Either the models need adjustment, or the physics is incomplete. Some galaxies break the rule. A few outliers have black holes much larger or smaller than expected. These exceptions are rare but instructive. They reveal conditions where the feedback fails or operates differently. Studying them helps refine the theories. The relationship extends beyond just mass. Black hole spin, galaxy morphology, and other properties also correlate. The entire system evolves as a unit, not as separate components. The black hole and galaxy are deeply interconnected. This connection might hold the key to understanding cosmic structure formation. Galaxies are not just collections of stars. They are complex systems where dark matter, gas, stars, and black holes all interact. Each component affects the others. The mass relationship is one visible sign of this deeper unity. As Webb continues observing earlier and earlier systems, it tests whether the relationship holds all the way back to the first galaxies. If it breaks down at some point, that would reveal when and how the feedback mechanisms first developed. If it holds forever, that would suggest something fundamental about the universe itself enforces the ratio. For now, the mystery deepens with each observation. The black hole-galaxy relationship appears universal across space and time, yet we still do not truly understand why. The first stars that ever ignited were monsters, 300 times more massive than our star, shining millions of times brighter, burning through their fuel in just a few million years before detonating in cataclysmic explosions. These population 3 giants were nothing like any star we see today. Stars form when gas clouds collapse under their own gravity. As the cloud contracts, it heats up. Eventually, the core becomes hot and dense enough for nuclear fusion to ignite. Hydrogen atoms fuse into helium, releasing energy. The star is born. The temperature needed for fusion depends on how efficiently the gas can radiate heat. Heavy elements like carbon and oxygen are excellent coolants. They absorb energy and re-emit it as infrared radiation, allowing the gas to cool and collapse further. But the first gas clouds contained no heavy elements, only hydrogen and helium from the Big Bang. Without efficient cooling, the clouds remained hot. Hot gas resists collapse due to thermal pressure. To overcome that pressure required more mass, much more. The minimum mass for population 3 star formation was probably 30 times our stellar mass. The typical mass was likely 100 or more. These giants collapsed from gas clouds weighing up to 300 stellar masses. Their cores burned at incredible temperatures, tens of millions of degrees. Fusion proceeded at furious rates, consuming hydrogen faster than smaller stars could ever manage. The energy output was staggering. A single population 3 star shone with the light of 1 million modern stars. Their surface temperatures reached 100,000 degrees. For comparison, our stellar surface sits at 6,000 degrees. The population 3 stars glowed blue-white, almost ultraviolet. Their intense radiation ionized everything nearby. These giants lived fast and died young. A 300-mass star burns through its hydrogen fuel in just 3 million years. Then it fuses helium into carbon, carbon into oxygen, all the way up to iron. Each stage proceeds faster than the last. The entire lifetime from birth to death spans perhaps 5 million years. When fusion produces iron, the end is near. Fusing iron requires energy rather than releasing it. The core cannot sustain itself. Gravity wins. The core collapses in less than a second, then rebounds in the most powerful explosion in the universe. A pair instability supernova. These explosions completely destroy the star. Nothing remains. No neutron star, no black hole. The entire star is blown apart, scattering its newly created elements across space. Carbon, oxygen, nitrogen, magnesium, silicon, iron, the building blocks for everything that follows. The explosion's energy was phenomenal. A single pair instability supernova could outshine an entire galaxy for months. The shockwave plowed through surrounding gas at thousands of miles per second, triggering new star formation in its wake. Population 3 stars also produced the first dust. Heavy elements condensed in the cooling supernova ejector, forming microscopic grains. This dust would later play a crucial role in star and planet formation, allowing gas clouds to cool more efficiently. Some population 3 stars might have formed black holes instead. If the star was massive enough, the core collapse could create a black hole directly. These would be the first black holes in the universe, potentially serving as seeds for later supermassive black holes. The radiation from population 3 stars triggered reionization. Their ultraviolet photons split hydrogen atoms throughout the universe. Each star created a bubble of ionized gas around itself. As more stars formed, the bubbles grew and merged until the entire cosmos was ionized. Without population 3 stars, the universe would look completely different. They created the first heavy elements, enabling later generations of smaller, longer-lived stars. They ionized hydrogen, making the universe transparent. They may have seeded black hole formation. Every structure we see today traces its origins to these ancient giants. Webb may have finally detected them in galaxy LAP-1b. The spectral signature matches theoretical predictions. Low metallicity, specific emission lines, the right age and distance. If confirmed, it is one of the most important astronomical discoveries ever made. Finding more population 3 stars is a top priority. Each detection would reveal how these monsters formed, how many existed, how they died. Every piece of information constrains models of the early universe, but they remain incredibly difficult to observe. They existed so long ago that their light is extremely redshifted and faint. Even with gravitational lensing magnification, only the brightest clusters are detectable. Most population 3 stars will remain forever beyond our reach, lost in the darkness of cosmic time. Yet their legacy surrounds us. Every atom in your body heavier than hydrogen was created in stars. The very first atoms came from population 3 stars. You are made of their remains. Ancient stardust, forged in the first light of creation, now conscious and looking back across time to see its origins. The universe built itself from the ashes of giants. Before reionization, the universe was blind. A thick fog of neutral hydrogen filled all of space, blocking ultraviolet light from traveling any distance. Then the first stars ignited and everything changed. Neutral hydrogen is transparent to visible light but opaque to ultraviolet. When an ultraviolet photon hits a neutral hydrogen atom, the electron absorbs the energy and gets knocked away. The atom becomes ionized. This process repeated trillions upon trillions of times across billions of years. Each ionized atom created a cascade. Free electrons could ionize nearby atoms through collisions. The radiation from one star could ionize hydrogen across thousands of light years. Bubbles formed and expanded at incredible speeds. The transformation was not gentle. Ionization heats gas to 10,000 degrees. The entire intergalactic medium went from cold and neutral to hot and ionized. This heating affected everything. It changed how gas flowed between galaxies. It influenced where new stars could form. It altered the large-scale structure of the universe itself. Webb observations reveal the transformation happened in stages. Different regions ionized at different times. Some areas near bright quasars ionized early. Other regions, far from any stars, remained neutral much longer. The universe looked like Swiss cheese, with ionized bubbles scattered through a neutral background. The topology matters because it affected subsequent galaxy formation. Gas in ionized regions behaves differently than gas in neutral regions. Ionized gas has higher pressure, resisting collapse. Galaxies forming in ionized regions grow more slowly than those in neutral zones. Scientists track reionization through the Lyman alpha forest. This is a specific wavelength of light absorbed by neutral hydrogen. When astronomers observe distant quasars, they see absorption lines at different wavelengths. Each line corresponds to neutral hydrogen at a different distance. By mapping these lines, they reconstruct where neutral hydrogen existed at different times. The forest gets denser at higher redshifts. Farther back in time, more neutral hydrogen existed. Eventually, around redshift 7 or 8, the forest becomes completely opaque. This marks the end of reionization. Before this point, so much neutral hydrogen remained that ultraviolet light could barely travel. Current measurements suggest reionization completed between 650 million and 1 billion years after the Big Bang. But Webb keeps finding bright early galaxies that should have ionized the universe faster. The timeline does not match perfectly. Something is missing from our understanding. One possibility involves recombination rates. Ionized protons and electrons can recombine into neutral hydrogen. If recombination happened more frequently than models predict, more ionizing radiation would be needed. The process would take longer and require more sources. Another factor is the escape fraction. Not all ultraviolet radiation produced by stars escapes into intergalactic space. Some gets absorbed by dust within the galaxy. The escape fraction determines how much ionizing power each galaxy actually contributes. If early galaxies had lower escape fractions than assumed, they would ionize the universe more slowly. Dwarf galaxies may have dominated the process. Webb found they were far more numerous than expected. Each small galaxy contributed modest ionizing radiation, but their sheer numbers added up. They might have done most of the work, while larger galaxies got the credit. The transformation was irreversible. Once ionized, the universe stayed ionized. The density had dropped too low for neutral hydrogen to reform. Stars continued producing ionizing radiation, maintaining the ionized state. Today, the intergalactic medium remains hot and ionized, a permanent legacy of that ancient transformation. But the fog's removal allowed something profound. Light could finally travel across cosmic distances. Galaxies became visible to each other for the first time. The universe opened its eyes. Early galaxies looked nothing like the majestic spirals and smooth ellipticals we see today. They were chaotic, violent, irregular blobs of stars and gas barely holding themselves together. Webb images reveal this chaos in stunning detail. Galaxies from the first billion years show no organized structure, no spiral arms, no central bulges, just clumpy, asymmetric collections of bright regions scattered randomly across the system. These are not galaxies in the modern sense. They are proto-galaxies, systems still figuring out how to be galaxies, still undergoing the violent processes that will eventually create organized structure. Star formation concentrates in dense knots rather than spreading evenly. Each knot blazes with thousands or millions of young stars. They appear as bright spots in Webb images, sometimes separated by dark lanes where little formation occurs. The distribution seems random, lacking any coherent pattern. Turbulence dominated these systems. Gas moved chaotically rather than in ordered rotation. Shock waves from supernovas created more turbulence. Inflowing material from intergalactic space added angular momentum randomly. Nothing settled into stable orbits. Mergers were constant. In the crowded early universe, galaxies collided frequently. Each collision disrupted whatever structure existed. Gas clouds slammed together, triggering intense star formation. Stars from both systems mixed. Dark matter halos merged, creating even more gravitational chaos. The velocities inside these galaxies were extreme. Gas moved at hundreds of miles per second. Stars orbited at random angles, rather than in a coherent disk. The systems had not yet relaxed into equilibrium. Gravity had not yet organized the chaos into order. This violence explains the extreme star formation rates. Collisions and turbulence compressed gas clouds, triggering formation much faster than would occur in stable systems. The chaos was productive. It built stars rapidly even as it destroyed any emerging structure. But the chaos was temporary. Over hundreds of millions of years, processes worked to calm these systems. Energy dissipated through radiation. Stars settled into more circular orbits through gravitational interactions. Gas lost angular momentum and fell toward the center, forming disks. By 1 to 2 billion years after the Big Bang, recognizable structures began appearing. Some galaxies developed disk-like features. Others showed signs of central concentrations. The transition from chaos to order was underway. Dark matter halos provided the framework. These invisible structures were smoother, more organized than the visible matter. As galaxies evolved, the visible matter gradually conformed to the shape of its dark matter halo. The halo acted like a mold, guiding the galaxy into its final form. Rotation helped. As systems spun, conservation of angular momentum naturally created disk shapes. Material settling into the disk gained circular orbits. Over time, the disk became the dominant structure, organizing the chaos into something recognizable. But many early galaxies never completed this transition. Mergers destroyed them before they could settle. Their stars and gas got absorbed into larger systems. The galaxies we see today are survivors, systems that managed to avoid destructive collisions long enough to develop stable structures. Some ancient chaos remains visible even now. Irregular galaxies in the modern universe show what early galaxies looked like. They lack organization, showing clumpy star formation and asymmetric shapes. They are evolutionary throwbacks, galaxies that never settled down. The Milky Way was once chaotic too. Simulations show our galaxy formed through multiple mergers of smaller systems. Each merger added stars and gas, gradually building the structure we see today. The smooth spiral we inhabit is the product of billions of years of evolution. But in Webb's images, we see galaxies still trapped in chaos, frozen in time at their moment of formation. Wild, turbulent, violent. This is how all galaxies begin. This is what we evolved from. Order emerged from chaos through time and gravity. Oxygen and carbon appeared in the universe faster than they should have. Webb detected these elements in galaxies barely 300 million years old. That is not enough time. Here is the problem. Heavy elements form inside stars. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen. Each step requires higher temperatures and pressures. Only massive stars reach the conditions needed to create elements heavier than carbon. Then the star must die, explode as a supernova, scatter those newly created elements across space. That enriched material must then condense into new stars. Only then do telescopes detect oxygen and carbon in stellar spectra. This entire process takes time. Massive stars live just a few million years before exploding, but the gas must cool, collapse, and form new stars from the enriched material. That adds tens of millions of years. The full cycle, from initial star formation to detectable enrichment, requires at least 50 to 100 million years. Webb found oxygen in galaxies 280 million years after the Big Bang. The math barely works. The universe had just enough time for one cycle of stellar birth, death, and rebirth. Maybe 2 cycles, if everything happened with perfect efficiency. But the oxygen abundance is not trace amounts. It is measurable, significant. Multiple stellar generations had to occur. That requires multiple cycles. The timeline gets impossibly tight. Population: 3 stars might provide the answer. These massive first stars died in pair instability supernovas, completely destroying themselves. Each explosion scattered enormous quantities of heavy elements. A single 300-mass star could enrich its surroundings more than dozens of modern supernovas. If population 3 stars dominated early star formation, they could enrich the universe much faster than current models assume. Their extreme masses and powerful explosions accelerated the process. What normally takes hundreds of millions of years happened in just a few tens of millions. Another possibility involves the initial mass function. If early star formation was top-heavy, producing mostly massive stars, enrichment would proceed rapidly. Each massive star lives fast and dies in a metal-producing supernova. The ratio of massive to small stars determines enrichment speed. Current observations cannot distinguish between these scenarios. We see the oxygen and carbon. We know they exist too early, but we cannot yet observe the stars that created them. Population 3-star detection remains tentative, unconfirmed by peer review. The distribution of elements also matters. Early enrichment was not uniform. Supernovas scattered metals in specific directions, creating enriched pockets surrounded by pristine gas. Some regions gained heavy elements quickly, while others remained metal-free much longer. This patchiness affected subsequent star formation. Metal-enriched gas cools more efficiently. It forms stars more easily and at lower masses. Regions with metals started producing solar-type stars, while metal-free regions continued making population 3 giants. Over time, mixing spread the metals throughout each galaxy. Turbulence, galactic winds, and mergers distributed the enriched material. Eventually, the entire system reached similar metallicity levels. But in the earliest epochs, huge variations existed within individual galaxies. Webb spectroscopy measures specific emission lines corresponding to ionized oxygen and carbon. These lines appear clearly in the infrared spectra of distant galaxies. By measuring their strength, astronomers calculate elemental abundances. The abundances are low compared to modern galaxies. Early systems show 2% the metallicity of our star. But 2% is not zero. It represents substantial enrichment. And it appeared remarkably quickly. This rapid chemical evolution challenges models of cosmic chemical enrichment. Models predict gradual increases in metallicity over billions of years. Instead, we see significant enrichment within hundreds of millions of years. The universe bootstrapped itself chemically faster than we thought possible. Each new Webb observation refines our understanding. More distant galaxies push back the timeline of enrichment. More detailed spectroscopy reveals additional elements: nitrogen, neon, sulfur. Each detection constrains formation models. The youngest chemical elements tell a story of rapid stellar cycling, of efficient mixing, of a universe in a hurry to create the building blocks of planets and life. Chemistry happened fast because stars lived and died fast. The ancient cosmos was a forge, rapidly producing the ingredients needed for everything that followed. Some black holes might never have been stars at all. They could have formed directly from collapsing gas clouds in the early universe, born massive from the start. This is the heavy seed scenario. And it might explain the impossible black holes Webb keeps finding. Normal black holes form from stellar death. A massive star exhausts its fuel. The core collapses. If the core exceeds 3 stellar masses, nothing stops the collapse. It forms a black hole. These stellar mass black holes then grow by accreting matter and merging with other black holes. But this pathway is too slow. Even growing at the maximum rate, a stellar mass black hole cannot reach 1 billion masses in less than 1 billion years. The math does not work. Yet, we see billion mass black holes existing just 570 million years after the Big Bang. Heavy seeds solve this problem. If black holes start much larger, maybe 100,000 stellar masses, they have a massive head start. Growing from 100,000 to 1 billion requires far less time. The timeline works. But how do you form a 100,000 mass black hole without stars? Through direct collapse of gas clouds. In the early universe, conditions were different. Extremely massive gas clouds existed, weighing hundreds of thousands of stellar masses. Normally, such clouds would fragment into smaller pieces, each forming an individual star. Fragmentation prevents single massive objects from forming, but fragmentation requires cooling. Gas must radiate away energy to collapse further. If something prevents cooling, the cloud stays hot. It contracts as a single unit instead of breaking apart. What prevents cooling? The absence of molecular hydrogen. This molecule forms when two hydrogen atoms bond together. It is an excellent coolant, radiating energy efficiently. Gas with molecular hydrogen cools and fragments. Gas without it stays hot and collapses intact. Intense ultraviolet radiation from nearby sources can destroy molecular hydrogen. The radiation splits the molecules apart before they can cool the gas. If such radiation bathes a collapsing cloud, it stays hot and forms a single massive object. That object is too massive and too hot to be a star. Nuclear fusion cannot stabilize it. The radiation pressure exceeds the gravitational binding. The object is fundamentally unstable. It collapses directly into a black hole without ever igniting as a star. This creates a black hole weighing 100,000 or more stellar masses, right from the start. No stellar evolution required, no waiting for growth through accretion. The black hole is born massive. Computer simulations demonstrate this process works. The conditions are extreme and rare, but they existed in the early universe. Pristine gas clouds in specific environments could undergo direct collapse. The simulations produce black holes in the exact mass range needed to explain observations. Evidence for heavy seeds comes from the mass relationships Webb observes. Some early black holes outweigh their host galaxies. This is backwards from normal systems. It suggests the black hole formed first, then attracted gas to build a galaxy around itself. Heavy seeds predict exactly this configuration. The quasar J 1120 plus 0641 shows properties consistent with a heavy seed. Its mass, estimated over 1 billion stellar masses, appeared just 700 million years after the Big Bang. The feeding rate and spectral characteristics match theoretical predictions for a system that started with a massive seed. Alternative explanations exist. Maybe stellar mass black holes can grow much faster than the Eddington limit suggests. Super Eddington accretion, like seen in LID 568, might have been common. Multiple episodes of rapid feeding could accumulate enough mass quickly enough, or perhaps black hole mergers dominated early growth. If mergers happened frequently, black holes could build mass through addition rather than accretion. Each merger doubles the mass instantly. A few generations of mergers build supermassive black holes rapidly. Current evidence does not definitively prove heavy seeds exist. The observations are consistent with the theory, but other explanations remain possible. Distinguishing between scenarios requires more detailed observations. Future Webb programs will search for direct collapse black holes in formation. If we can catch one collapsing, we will confirm the mechanism. The spectral signature during collapse should be distinctive, different from either stars or accreting black holes. For now, heavy seeds remain the best explanation for many observations. They solve the timeline problem. They explain the mass relationships. They predict properties matching what we see. The theory works. Whether nature actually uses this pathway remains to be proven, but the possibility is profound. Black holes might form through multiple pathways, some from stars, some from direct collapse. The diversity of formation mechanisms creates the diversity of black holes we observe. The universe is more creative than we imagined. Gas is fleeing from ancient black holes at 1/5 the speed of light. Nothing in the modern universe compares to these violent outflows. Webb detected the signature in quasar spectra. Emission lines shifted significantly to shorter wavelengths. Blue shifted. That means the gas is moving toward us, moving fast. Analysis reveals velocities of 37,000 miles per second, 1/5 of light speed, confirmed through multiple observations. These are quasar-driven winds. The black hole's intense radiation pushes on surrounding gas. Photons carry momentum. When they hit atoms, they transfer that momentum. The atoms accelerate outward. More photons hit them. They accelerate more. The effect compounds. At close distances to the black hole, the radiation pressure is tremendous. Gas heated to millions of degrees by the accretion disk expands violently. Magnetic fields channel the flow, creating organized outflows rather than spherical expansion. The wind emerges in specific directions, often perpendicular to the accretion disk. The mass outflow rate is staggering. These winds carry away hundreds or thousands of stellar masses per year. That is comparable to or exceeding the rate at which the black hole feeds. The black hole ejects as much or more material than it consumes. This seems wasteful. Why would a black hole expel the very material it needs to grow? But the effect is actually regulatory. The wind removes gas that would otherwise fall in. This limits the feeding rate. It prevents the black hole from growing too large, too fast. The wind also affects the surrounding galaxy. When the high-speed gas slams into the interstellar medium, it creates shock waves. The shocks heat gas to extreme temperatures. Hot gas cannot collapse to form stars. Star formation throughout the galaxy gets suppressed. This is AGN feedback in action. The black hole, through its winds, controls the galaxy's evolution. It prevents the galaxy from forming too many stars. It maintains the mass relationship between black hole and galaxy. The wind is the mechanism that enforces the correlation. In the early universe, these winds were stronger than today. Young quasars fed more vigorously, producing more intense radiation. The resulting winds reached higher velocities and carried away more mass. The feedback was more powerful, more dramatic. Some winds are enriched with heavy elements. Spectroscopy reveals carbon, oxygen, nitrogen in the outflowing gas. These elements formed in stars and somehow got near the black hole before being ejected. The wind carries them far into intergalactic space, enriching regions far from any stars. This metal enrichment affects cosmic evolution. Pristine gas in intergalactic space gets polluted by metals from quasar winds. Future generations of galaxies form from this enriched material. They start with higher metallicity, forming different types of stars than earlier generations. The geometry of the wind matters. Not all directions experience the same outflow. Gas near the accretion disk's equator might be shielded from direct radiation. The strongest winds emerge from the poles. This creates a bipolar outflow pattern, jets of gas shooting in opposite directions. Sometimes these jets are visible as actual structures. Webb images show elongated features extending from early quasars. These are the winds made visible, glowing from the energy they carry. They stretch for thousands of light years, plowing through intergalactic space. The terminal velocity, the final speed the gas reaches, depends on the quasar's luminosity. Brighter quasars drive faster winds. The brightest ancient quasars launched gas at nearly half the speed of light. These are some of the fastest bulk motions of matter anywhere in the universe. But the winds are temporary. They last only as long as the quasar remains active. When the black hole quiets down, entering a dormant phase, the winds cease. The gas they expelled continues moving outward, but no new material joins the flow. The effect lingers, but eventually fades. Tracking these winds helps astronomers understand black hole feeding cycles. The wind properties reveal the accretion rate, the radiation field strength, the magnetic field configuration. Each detail constrains models of how black holes grow and affect their environments. What happens when these ultra-fast winds collide with slower-moving gas? The interaction creates turbulence, mixing, and additional heating. It might trigger or suppress star formation depending on local conditions. The full effects remain under investigation, but one thing is clear: these winds are not gentle breezes. They are cosmic hurricanes, tearing through space at relativistic speeds, reshaping galaxies, enriching the universe. They are the breath of black holes, exhaled with tremendous violence. Webb keeps finding something unexpected in early galaxies: incredibly dense clusters of stars, packed so tightly they should tear themselves apart. Yet there they are, stable, brilliant, defying expectations. These are not like globular clusters in the modern universe. Those contain thousands to millions of old stars, spread across light years. These ancient clusters contain thousands of young, massive stars, compressed into regions just a few light years across. The density is extreme. Stars orbit so close together that collisions must be frequent. When two stars collide, they merge into a larger star. This process, called runaway merging, should quickly build extremely massive stars in the cluster center. Some clusters might contain stars exceeding 1,000 stellar masses. Nothing like them exists today. They would be incredibly bright, incredibly hot, incredibly unstable, living only hundreds of thousands of years before exploding catastrophically. These ultra-massive stars would dominate the cluster. Their radiation would heat surrounding gas, preventing new star formation. Their stellar winds would blow away loose material. When they finally explode, the supernova would disrupt the entire cluster, potentially destroying it completely. Yet the clusters persist. Somehow, they survive long enough for Webb to observe them billions of years later. Something stabilizes them against the forces trying to tear them apart. One possibility is that we are seeing the clusters during a brief phase. Maybe they last only a few million years before disruption. We catch them at this special moment because so many formed in the early universe. The probability of observing one is higher simply because there were more of them. Another idea suggests the clusters are bound by dark matter. If a small dark matter halo surrounds each cluster, its gravity helps hold everything together. The dark matter provides additional binding, preventing stars from escaping despite the intense radiation and stellar winds. The formation mechanism is puzzling too. How do you create such dense clusters? Normal star formation produces more dispersed systems. Gas clouds collapse and fragment, spreading stars across larger regions. Getting thousands of stars packed into a few light years requires special conditions. Extreme gas densities in the early universe might explain it. If collapsing clouds were far denser than today, the resulting star clusters would be correspondingly compact. The higher density environment naturally produces tighter systems. Simulations show that rapid gas infall can build dense clusters. If gas flows into a region faster than it can form stars, density builds up. When star formation finally triggers, it happens all at once in a concentrated burst. All the stars form nearly simultaneously in a tiny volume. These clusters might be the progenitors of globular clusters. Modern globulars are old, dating back billions of years. They could be the surviving remnants of these ancient dense clusters. The most massive stars died early, their supernovas expelled gas, and the remaining stars spread out into the configurations we see today. But many ancient clusters probably did not survive. The most extreme ones likely disrupted themselves. The supernova of a 1,000 mass star releases enough energy to unbind the entire cluster. The stars scatter, becoming part of the general galactic population. The metallicity of these clusters provides clues. Some show very low metal content, suggesting formation from nearly pristine gas. Others already show enrichment, indicating they formed after earlier stellar generations died. This diversity reveals that clusters formed throughout the first billion years. Their contribution to reionization might be significant. Each dense cluster produces enormous amounts of ultraviolet radiation, The tight packing means the radiation escapes efficiently, not getting absorbed by internal gas. These clusters could be highly effective at ionizing their surroundings. Webb's infrared vision reveals individual clusters that Hubble could never see. The detail is extraordinary. Astronomers can measure the cluster size, star count, total luminosity, and spectral properties. Each measurement refines theoretical models. Future observations will track these clusters over time. Well, not literally watching them evolve, but observing similar clusters at different distances to see different evolutionary stages. This builds a picture of how they change, what happens to them, what they become. The existence of these clusters challenges assumptions about star formation. They show that early processes could create structures unlike anything in the modern universe. The physics was the same, but the conditions were so extreme that outcomes differed dramatically. Every strange cluster Webb finds adds another piece to the puzzle. Together, they reveal an early universe far wilder and more diverse than we expected. A universe where extreme conditions created extreme objects. A universe barely recognizable compared to the orderly cosmos we inhabit today. Galaxies are not scattered randomly through space. They follow a vast, intricate pattern, a cosmic web of filaments and nodes spreading across billions of light years. This structure is the skeleton of the universe. Dark matter formed it. During the Dark Ages, tiny density fluctuations grew under gravity. Regions slightly denser than average attracted more material. They grew denser still. The process amplified itself, creating a hierarchy of structures. The dark matter organized into halos. Small halos formed first, then merged into larger ones. The mergers were not random. They followed the initial density pattern, creating a web-like distribution. Matter concentrated along filaments, connecting massive nodes. Think of it like a three-dimensional spider web. Thick strands of dark matter span the cosmos. Where multiple strands intersect, massive clusters form. Between the strands lie vast, empty regions, voids containing almost nothing. Normal matter, the gas and stars we can see, follows the dark matter. Gas flows along the filaments, funneling toward the nodes. Galaxies form where filaments intersect. The visible universe traces the invisible structure beneath. Computer simulations recreate the cosmic web with stunning accuracy. Starting from measured fluctuations in the cosmic microwave background, simulations evolve forward billions of years. They show how structure grows from nearly uniform beginnings into the complex web we observe. The similarity between simulations and observations is remarkable. The web's appearance, the void sizes, the cluster masses, all match predictions. This confirms our basic understanding of how gravity shapes the universe. But the web is not static. It continues evolving. Filaments grow, nodes accumulate more mass, voids expand as space itself stretches. The structure we see today is just a snapshot of an ongoing process. Galaxy surveys map the web's large-scale structure. By measuring positions and distances to millions of galaxies, astronomers reconstruct the three-dimensional web. The results reveal filaments stretching hundreds of millions of light years, connecting clusters separated by vast distances. The Milky Way sits within a filament. Our local group of galaxies moves along this filament, pulled toward a massive node called the Virgo cluster. We are part of the web, flowing through it like a log in a river. The cosmic web affects galaxy properties. Galaxies in dense nodes experience frequent interactions and mergers. These violent events trigger star formation but also disrupt galaxies. Cluster galaxies differ significantly from isolated field galaxies. Galaxies in filaments experience constant inflow of gas from the web. This fresh material fuels ongoing star formation. Filament galaxies often appear actively star-forming, blue and gas-rich. They have access to plentiful fuel. Void galaxies live in near-perfect isolation. They rarely interact with neighbors. Their evolution proceeds undisturbed. They form stars slowly, exhausting their internal gas without replenishment. Many void galaxies are red, old, and quiet. This environmental dependence is called galaxy environment correlation. Where a galaxy lives determines how it evolves. The cosmic web structure directly influences galactic properties across billions of years. In the early universe, the web was less developed. Filaments were thinner, nodes were smaller, but the basic structure existed even then. Webb observations reveal early galaxies clustered along developing filaments, following the same pattern that dominates today. The web grows through hierarchical merging. Small structures merge into larger ones. Filaments connect into thicker strands. Nodes combine into superclusters. This bottom-up growth continues indefinitely, but dark energy opposes the growth. The accelerating expansion of space works against gravity. Eventually, expansion will overcome gravity's pull. Structure growth will stop. The web will freeze in its current configuration. Billions of years from now, the web will start dissolving. Expanding space will stretch filaments until they break. Nodes will drift apart, losing connection to the wider web. Our cosmic neighborhood will become increasingly isolated. But for now, the web thrives. It channels matter, guides galaxy formation, shapes cosmic evolution. It is the architecture underlying everything, the framework upon which reality is built. Understanding the web means understanding the universe. Every galaxy, every cluster, every structure traces its origin to this ancient pattern. A pattern born from quantum fluctuations in the first moments after the Big Bang. A pattern evolved through gravity across cosmic time. A pattern revealed through painstaking observations and brilliant simulations. The cosmic web is the universe's circulatory system. Dark matter forms the vessels. Gas flows through them. Galaxies are the cells, living and dying within the greater organism. We inhabit one cell, looking outward, trying to comprehend the whole. Beyond the observable universe lies something we can never see. The question is, what? The observable universe ends at the particle horizon. Light from beyond this boundary has not had time to reach us. But that does not mean nothing exists there. It means we are fundamentally limited in what we can observe. The simplest possibility is more of the same. Beyond our horizon, the universe continues. Same laws of physics, same types of galaxies and stars, just more space, extending indefinitely in all directions. This is the infinite universe model. If the universe is infinite, then everything that can happen does happen somewhere. Every possible arrangement of matter exists. Infinite space contains infinite possibilities. Somewhere, impossibly far away, another Earth exists. Another you, reading these exact words, not metaphorically, literally. Infinite space guarantees it. But maybe the universe is not infinite. Maybe it curves back on itself like the surface of a sphere. Travel far enough in one direction, and you return to your starting point. This is a finite but unbounded universe. It has no edge, but also no infinite extent. Detecting this curvature requires measuring the universe's geometry. Scientists compare the apparent size of the cosmic microwave background fluctuations to their actual size. If the universe is curved, sizes will appear distorted. Current measurements show the universe is flat, or very nearly so. The curvature, if any, is incredibly slight. A flat universe extends infinitely. Curvature would indicate finite size. The measurements strongly favor infinite extent, but the precision is limited. A very slight curvature could exist, undetectable with current technology. Beyond the observable universe, conditions might differ. The laws of physics might vary. Constants we consider fundamental might have different values. This is the multiverse hypothesis. Our observable universe is just one region in a much larger structure where properties vary from place to place. Some versions of inflation theory predict this. During the rapid expansion after the Big Bang, different regions inflated by different amounts. Each region became a separate universe with potentially different physical properties. These universes exist beyond each other's horizons, forever separated. The multiverse is controversial. It makes predictions we cannot test. If something is fundamentally unobservable, is it even science? Critics argue the multiverse is philosophy. not physics. Supporters counter that it emerges naturally from our best theories. String theory also suggests multiple universes. The theory has many possible solutions, each corresponding to a universe with different properties. All solutions might be realized somewhere in a vast multiverse landscape. Another possibility involves quantum mechanics. Every quantum measurement splits reality into branches. Each possible outcome occurs in a separate branch. These branches constitute parallel universes, all equally real, all beyond our observation. But maybe thinking about what comes after is asking the wrong question. Maybe the universe has no after. Maybe the observable universe is all that exists, and beyond our horizon is literally nothing. Not empty space, not void, nothing at all. The universe could be fundamentally finite, with the edge being a genuine boundary beyond which reality itself does not exist. This seems impossible to our intuition. How can reality just stop? What would stop it? But our intuition evolved to handle everyday scales. Cosmic scales might operate by completely different rules. The universe might exist in higher dimensions. We perceive 3 spatial dimensions, but additional dimensions could be compactified, too small to notice. Beyond our observable universe, these extra dimensions might open up. Space could extend in directions we cannot even conceptualize. Time might behave differently beyond our horizon. The expansion rate could vary. Other regions might experience time faster or slower, or time might not exist there at all. Without change, without causality, time becomes meaningless. Dark energy dominates our universe's expansion, but its density might vary. Other regions could have stronger or weaker dark energy. This would create radically different cosmic evolution. Some regions might recollapse, others might expand so fast that even atoms get torn apart. We will never know for certain. The horizon is absolute. No signal can reach us from beyond it. No telescope, no matter how powerful, can see past this boundary. It is not a technological limitation. It is a fundamental property of space-time and light. Yet scientists continue theorizing, modeling, calculating, because even if we cannot observe beyond the edge, understanding the possibilities tells us about our own universe. It reveals the nature of reality itself. It shows what could be, even if we can never confirm it. The edge is not a wall. It is a limit of observation. Beyond it, something exists. We just do not know what. James Webb has revolutionized astronomy, but it is just the beginning. Next-generation telescopes will push even further, revealing secrets Webb cannot reach. The Nancy Grace Roman Space Telescope launches in the late 2020s, where Webb observes tiny patches of sky in exquisite detail. Roman will survey vast areas. Its field of view is 100 times larger than Webb's. It will map the cosmic web, find thousands of early galaxies, track dark energy's evolution. Roman's infrared vision matches Webb's wavelength range, but its survey speed is unmatched. It can observe the entire sky multiple times, building a comprehensive picture of how the universe evolved. Every galaxy, every quasar, every structure mapped and catalogued. On the ground, the extremely large telescope in Chile is under construction. Its mirror spans 128 feet across. That is more than 4 times Webb's diameter. The light-gathering power will be extraordinary. Ground telescopes face atmospheric distortion. Stars twinkle because air turbulence bends light. But adaptive optics systems compensate. They measure distortions thousands of times per second and adjust mirror shapes to cancel them. The result approaches space-based clarity. The extremely large telescope will directly image exoplanets. It will study the first galaxies in unprecedented detail. It will detect the faintest objects Webb cannot see. Construction continues. First light expected in the early 2030s. The square-kilometer array revolutionizes radio astronomy. Thousands of radio antennas spread across 2 continents create a telescope with a collecting area of 1 square kilometer. That is million square meters of detection surface. This array will map the 21-centimeter line of neutral hydrogen across cosmic history. It will track reionization in 3 dimensions. It will reveal the distribution of gas throughout the early universe. The cosmic dark ages might finally become visible through their radio signature. LISA, the Laser Interferometer Space Antenna, launches in the mid-2030s. 3 spacecraft flying in formation create a gravitational wave detector spanning millions of miles. It will detect supermassive black hole mergers like ZS7 as they happen in real time. Gravitational waves carry information light cannot. They travel through dust unimpeded. They reveal the masses and spins of merging black holes with incredible precision. LISA will open an entirely new window on the early universe. Spectroscopy advances push toward individual star detection in distant galaxies. Future spectrographs might resolve individual population 3 stars. We could study their properties directly instead of inferring them from integrated galaxy light. Artificial intelligence transforms data analysis. Machine learning algorithms sift through millions of spectra, identifying subtle patterns invisible to human analysis. AI finds rare objects, classifies galaxies, measures properties with superhuman precision and speed. Quantum sensors might enable new detection methods. Quantum entanglement allows measurements exceeding classical limits. Future telescopes might exploit quantum effects to detect fainter signals or measure positions with impossible precision. But technology alone does not drive discovery. Questions guide us. What are the little red dots? How did the first black holes form? When did the first stars ignite? How did galaxies become organized? Every answer raises new questions. Some mysteries might remain forever unsolved. The universe before recombination is opaque to light. The edge of the observable universe is unreachable. Certain questions might have no observable answers, yet the questions motivate us. They drive telescope construction, observation campaigns, theoretical work. Humanity's desire to understand overcomes incredible obstacles. We build instruments costing billions, operate them for decades, analyze data for lifetimes, all to answer fundamental questions about existence. The future of cosmic discovery is bright. Webb showed us the early universe in detail for the first time. It revealed that universe is stranger, more violent, more mysterious than we imagined. It raised as many questions as it answered. The next generation of telescopes will probe deeper. Romans surveying vast volumes, extremely large telescopes seeing fainter objects, square kilometer array mapping gas, LISA detecting gravitational waves. Each adds another piece to the puzzle, but the complete picture remains elusive. Each discovery opens new frontiers. Each answer suggests new questions. The universe guards its deepest secrets carefully. We are only beginning to understand. 13.8 billion years of cosmic history, from perfect darkness to galaxies and stars, from hydrogen and helium to planets and life, from quantum fluctuations to conscious beings asking how it all began. Webb lets us witness those earliest moments. See the first light. Watch the first structures form. Observe the processes that created everything we know. We stand at the edge of time, looking back toward the beginning. What NASA found there is more than galaxies and black holes. It is the story of creation itself. The tale of how nothing became something, how chaos became order, how the universe became conscious of itself. This is just the first chapter of that story. The next chapters will be even more remarkable, because the universe has not finished revealing its secrets. It has barely started. The edge of the universe is not the end of discovery. It is the beginning.